Welcome to this second video lesson on work, energy and power. Now, in this video lesson, I'm going to focus on the definition of energy and then one of the forms of energy that we use explicitly in high school science in the NSC, and that is namely gravitational potential energy. Now, in grade 7, you should have learnt about the different types of energy. The main types of energy: heat energy, potential energy, kinetic energy, electrical energy, etc. So in this video lesson, we're going to focus on gravitational potential energy and how to use the mathematical formula for gravitational potential energy to solve problems that involve gravitational potential energy. So let's start off with the definition of energy. So energy is the ability to do work. So the energy that an object possesses is its ability to do work. Now, when we looked at the scientific definition of work, we defined it as the transfer of energy. Now, that might sound like it's a little bit cyclic because we're using in the definition of energy, we're using the concept of work. And in the definition of work, we're using the concept of energy. So it is cyclic. We're not going to worry too much about that as long as we have a formal definition that we can use as a base. So we're going to focus on two main types of energy. The first one is going to be gravitational potential energy. And then in the next video lesson, we're going to focus on kinetic energy. And then in the lesson thereafter, we're going to put them together and we are going to work with what we call mechanical energy. So let's look at the definition of gravitational potential energy. It says here that gravitational potential energy is the ability that an object possesses to do work. Notice it's the same as this definition in the beginning. But now, why does it have the ability to do work? Well, it has the ability to do work due to its position in the Earth's gravitational field above ground level. Now, one should actually state this in a more general way, that the gravitational potential energy is the ability that an object possesses to do work due to its position in a gravitational field above the zero potential level in that field. Now, you can have a black hole that has got an immense gravitational field. You can have neutron stars, you can have planets, moons, asteroids. These are all astronomical entities with massive masses. All these objects will generate a gravitational field. And depending upon where you are in that gravitational field, your potential energy will vary. But for grade 8, we are going to use this definition, and we're going to use the Earth as the source of the gravitational field. Now, the formula for gravitational potential energy is the following. The gravitational potential energy is equal to the mass times gravity times the height. Now, if you've been observant, you should pick up that mass times gravity is in actual fact weight. Remember, we said weight is mass times gravity. So an object of mass m has a weight because of the fact that it's in a gravitational field. Now, if you want to move that object from one point in the field to another point in the field, you're going to have to apply a force that is at least equal to the weight, and probably bigger than the weight, especially if you're going to move it away from the object. And so this is why this mg occurs or appears in this formula, is because if you want to move an object of mass m, let's say this is an object of mass m, and you want to move it, now the gravitational field is in that direction and the surface of the planet is there, and you want to move this mass. If you move it without accelerating it significantly, then we would refer to this in physics as a quasi-static situation. You're moving it so slowly that the acceleration is basically zero. Then, because of the fact that the weight is acting down, the weight mg is acting down, you would have to apply a force that is equal in magnitude but opposite in direction, moving the object away from the surface of the planet, and that would mean that this force magnitude-wise would equal mg. Now, if we want to change the position of this object, we are going to move it over a distance d to another point there. Then that distance d is actually going to be equal to the change in the height of the object above the ground level. So therefore, when working with what we've learnt about work, big W, capital W equals force times distance. And in this case, the force would be mass times gravity, and the distance would be the change in height. Now, if we define the original position of the object as on the surface, then the change in height would be the actual height above ground level, and then we would get the simplified form. We would get that W, capital W, which is the work done, equals mg times h. And so this is the formula that we are going to use for potential energy, because the work that's being transferred to the mass is being transferred into the form of potential energy. So EP, which is, we use the little p, the subscript p for potential, the big E for energy, or we can also write it as, some people write it as U, or they write it as PE, potential energy. Either of these is fine. I just want to mention the fact that in physics you get different types of potential energy as well. You also get chemical potential energy, you get electrical field potential energy, you get, I think we mentioned chemical potential energy, nuclear, electrostatic potential energy. And so wherever there's a field, you're going to have a potential energy, even in a magnetic field. So now let's move on. So we are now going to use this formula, and we are going to put it into a formula triangle, which I like to do in grade 8. So here's your formula triangle. The potential energy is equal to mass times gravity times height. The potential energy is going to be measured in joules. This is very important. The mass in kilograms. But with G, we're going to change it. With G, we're not going to work with 10. We're going to work with 9,8 newtons per kilogram. Now, those of you who go into other resources might see that sometimes you'll see G as 9,8 meters per second squared. Now, that's not wrong. The beauty of science is that it teaches us to look at the same phenomena in different ways. So when we use 9,8 newtons per kilogram, we're viewing G as the gravitational field intensity. In other words, the strength of the field at that point. In other words, how many newtons of force is applied per kilogram. But that results in the object also accelerating. And that basically means that if your field intensity is 9,8 newtons per kilogram, then your acceleration would be 9,8 meters per second. Now, 9,8 meters per second is around about 35 kilometers per hour. So what that means is if you jump off a very high building, within the first second you're traveling around about 35 kilometers per hour. In the second second, your velocity is going to increase by another 9,8 meters per second, which is about 35 kilometers per hour, which means you'll be traveling at 70 kilometers per hour. And after the third second, you're traveling at over 100 kilometers per hour. That would be 105 kilometers per hour. Like they say, it's really not the speed that's dangerous, It's the stop at the end of your journey that is dangerous. So on that morbid note, let's take a look at some examples. So in your notes, I have the example here of determining the gravitational potential energy of a brick with a mass of 2 kilograms at a height of 6 meters above ground level. So, as you've been taught in physics, step number 1 is we write down the formula, EP equals mgh. We now substitute the values for mass, gravity, and height in there. Now, as I've just mentioned, we are not going to work with 10, we're going to work with 9,8. And so we're not going to get quite 120 joules. So please do not work with G equals 10 in the syllabus. So step number 2 is going to be the substitution step, where the potential energy is equal to 2 kilograms times 9,8 newtons per kilogram times 6 meters. So that gives us an answer of potential energy is equal to 117,6 joules. So what that means is that if we take this brick of mass 2 kilograms to a height of 6 meters above ground level in the Earth's gravitational field, then that brick has got stored energy in it. That brick is going to have stored energy of 117,6 joules. Now, that energy didn't come from just nowhere. It came from the fact that work was done to move that object, that brick, from ground level to 6 meters above ground level. So in a situation like this, we're going to define the lowest point as the zero potential. In other words, this point here is going to be the zero potential, because that is where we have defined the height to be zero. Now, with gravitational potential energy, actually with any potential energies, your zero potential is relative. You can define it in a particular system in a different way. So in this syllabus, we're going to define our lowest points in a system as the zero potential to make life easier for us. So if we now look at the next problem, it says determine the height of a brick with a mass of 12 kilograms if it has a gravitational potential energy of 2,400 joules. So if we look here, we have the height of the brick is unknown. The mass, it's a very big brick, is 12 kilograms, and we've been given the energy. So if we now go and use the formula triangle, we've got the formula triangle here. We have that EP is mass times gravity times height. Remember, potential energy is measured in joules, height in meters, G is 9,8, and the mass is in kilograms. So now what are we looking for? We are looking for to determine the height. So we are looking for the height. The height is what we're looking for. So step number one is we are going to say, okay, the height equals, I'm going to block that out, the potential energy over mass times gravity. Keep in mind, the vertical lines in a formula triangle represent multiplication, and the horizontal lines division. So the height is potential energy divided by mass times gravity. And so there is your first mark for your formula step. Then we substitute in the height. This is step number 2 now. The height is equal to the potential energy, which is 2,400 joules. We've been given that. The mass is 12 kilograms. But now we're not going to use 10, we're going to use 9,8 newtons per kilogram. And my advice to you is to put that in a bracket. Then step number 3, if we work it out, we say 2,400 divided by bracket 12 times 9,8, close bracket. And that should give us an answer of 20,4 1 meters. So there's the allocations of the second and the third mark. Now, this is an example of where we've manipulated the standard formula of E equals mgh in order to make h the subject of the formula. So let's now move on to another problem. So here we have now determine the gravitational field strength of another planet if a 1,000 kilogram spaceship at a height of 100 meters above the surface of the planet has a gravitational potential energy of 5 million joules. So we've now, this is number 3, we have the mass of the spaceship, we have its height, we're told what its gravitational potential energy is, we want to know what the gravitational field strength is on that planet. So pause the video and try and work this out using the formula triangle that we have given you. Okay, so now looking at the solution, we have that we need to find G. So using this formula triangle here, we are now going to work out G. Now, I'm going to, for the sake of clarity, I'm going to redraw it. So our potential energy is mgh. Right, so this is joules, this is meters. Okay, this is newtons per kilogram, but now we must be careful. We are not on Earth. So G does not equal 9,8 newtons per kilogram. We're going to have to find it, and the mass will be in kilograms. So we are looking for G. So we're going to write out step number 1. Step number 1 is the formula step. G is going to be the potential energy over mass times height. So G is going to be the potential energy over mass times height. That's step number 1. Step number 2, we substitute in. So we know that G is 5 million joules. The potential energy is 5 million joules. The spaceship has a mass of 1,000 kilograms. And we are told that it's at a height, we can see here, it's at a height of 100 meters. So we're going to put in the 100 meters. And so when we do that, we're going to see step number 3, we've got 5 million divided by 100,000, and that gives us that G is 50 newtons per kilogram. Now, so mark allocation, mark for step number 2, the substitution step, mark for step number 3. So we see there's 50. We are going to work with newtons per kilogram. Now, this means that the gravitational field is stronger than on Earth. So obviously this planet's mass and dimensions are different. In grade 11, you will actually work with the formula, and I'm going to show it to you. Little g equals big G, mass of the source of the gravitational field over the distance squared. So this is a universal gravitational constant, which is true throughout the universe. This is the mass of the actual planet or astronomical object that is the source of the gravitational field. And d is how far away one is from the center of the planet. But that we will do in grade 11. So we've now covered the 3 different types of problems that you could get in your tests and exams. We will revisit this when we do mechanical energy calculations as well as conservation of mechanical energy calculations. So thank you for listening to this video lesson. In the next video lesson, we're going to look at the other form of energy that we're going to work with, namely the energy of motion or kinetic energy. Thank you.